Welcome everyone to the Princeton Robotics seminar. As a quick reminder to those of you who are undergraduate students taking the robotics minor, the check-in for the robotics seminar is on the robotics seminar website, and you need to make sure that you check in and record your attendance before you leave these premises today. All right, so it's my pleasure to introduce our speaker for today. We are very fortunate to have with us our very own Princeton colleague, Parastoo Abtahi, who is an assistant professor in the computer science department, working on human-centered devices of various kinds and using technology to augment the human experience and to help people better interact with their environments, with various types of problems and tasks and systems, including robotics. I find that her work is, on the one hand, fascinating, and on the other, extremely complementary to a lot of the questions and the research problems that we think a lot about in the robotics crowd. So I'm very excited for some of the connections that I'm sure she's going to draw between our various research interests and hopefully the follow-up discussions that will happen after the talk. I'll just say a few words about Parastoo's trajectory. She got her undergraduate degree in the University of Toronto in electrical and computer engineering. And then she got her PhD at Stanford University in computer science. And before coming to Princeton, she spent some time as a research scientist at Meta Reality Labs research. So she comes with a very nice and sort of comprehensive trajectory and experience spanning computer science, electrical engineering, systems thinking, but also human-centered design. And her work has already been recognized with multiple awards, including the Google Research Scholar Award and multiple awards for best paper and best paper mention at multiple human-computer interaction sort of top conferences like ACM's Chi Conference and WIST, which I'm told most people who are not in human-computer interaction mispronounce, but now I can consider myself an insider because I just learned from Parastoo how to pronounce it. All right, so with that, thank you so much, Parastoo, for being here, and take it away.
Thanks so much, Jaime, for the introduction. Can everyone hear me in the back? Okay, excellent. Thanks so much for the introduction, Jaime. I'm very excited to be here and meet you all and talk about some of the work we've been doing. I want to preface this and reiterate that I'm not a roboticist. My field is human-computer interaction, so I think a lot about interaction design. I co-direct the Princeton HCI group here, and my lab is called Situated Interactions Lab. So we think a lot about how future of computing will be situated in physical spaces. And of course, robots are a big part of that. So today I'll be talking about some of the work we've been doing at the intersection of robotics and augmented reality and virtual reality. So when I started my PhD, this was 2016, there was a very, I don't want to say hype, but excitement around virtual reality. Even though VR had been around for decades, there were a lot of commercial VR headsets that were coming out, and that was a very exciting time to be doing VR research. And so I like to start off by some examples of VR applications that I find exciting beyond entertainment and gaming, because when I say VR, people immediately think of gaming, and I'd like to kind of start off by some applications that I'm excited about in virtual reality. One category is, of course, experiences that we couldn't have otherwise. So things that we couldn't have access to. For example, you could experience what it's like to go on the International Space Station. Anything that you create that's 3D, VR is very well suited for designing 3D content. And of course, there are a lot of learning opportunities. Here, I'm showing an example of people manipulating molecular structures that take advantage of our innate spatial reasoning skills. But anything that requires a simulated environment, maybe it's dangerous to do the task first in the physical world. You want to do some training in VR. These are all really great examples. But has everyone here tried a VR headset? Can I get a raise of hands? Okay, almost everyone. So if you've tried a commercial VR headset, visually you saw a lot of exciting content. The tracking has gotten a lot better. The field of view is great. The rendering quality is much improved. But when you think about your interactions in terms of your sense of touch, at best, what you were doing is you were holding a controller like this that vibrated once in a while in your hand. And so there's really this gap of how much haptic rendering we can do in commercial VR headsets today. And that's what I was thinking about at the beginning of my PhD, and thinking about how we interact in the physical world is we touch surfaces, we feel their textures. When we grab an object, we can tell its stiffness, its weight. And all of this enables the dexterous manipulations and improvisations that we do with physical objects around us. But when we put on a VR headset, maybe we see something exciting visually, but when we try to reach out and touch it, there's nothing there for us to feel and interact with in the same way. So I started my PhD with kind of an out there idea of what if we had a swarm of drones that kind of puppeteered our haptic interactions in VR. So let's say I could predict that someone was going to touch this spaceship. And what if I could have these drones look around in the space looking for either a 3D printed object that resembled this object, or everyday objects that have the same kind of physical geometrical properties, that then when the user reaches out to touch the virtual object, they're presented with a physical object. So I started to do this. One application could be something like an e-commerce application. The graphics here are not great. This is now a few years old, but you get the idea. There's a scarf here that I want to purchase. I want to be able to feel the texture of the scarf. I want to be able to feel the weight of the hanger. And these are the things that if you put on any virtual simulator right now, you won't be able to experience. So my goal was to use drones to be able to create these haptic sensations. So I started off by just one drone. So this is a custom-built racing quad that I've wrapped around this meshed cage, which is lightweight but protects people's fingers from hitting the propellers. And I integrated it in the e-commerce application that I showed. So we were able to track the user's hand, their head, and within the virtual simulation, we could send waypoints to the drone to autonomously navigate to based on what patches of the virtual world we could render haptically. So this is a video of me trying this out, virtual application. So we have fabrics around the drone, and I can reach out, and depending on what object I touch, I get the correct mapping. And then we have also this 3D printed block that's attached to the drone. As you noticed here, it was not a perfect system. And the drone especially was very difficult to position precisely in space. And I'm in VR, so I can't see where the drone actually is. So even if it's off by a millimeter, it means that I'm not going to end up touching it and interacting with it. And of course, we could make the system very complicated and ensure that the position accuracy is better. But really, what I want to highlight in this talk is that whatever haptic device that we built is going to have some limitations, whether it's the controller that I mentioned earlier, whether it's a glove, or any category of encounter-type haptic devices, which were traditionally grounded robotic arms that moved around and presented a surface whenever someone encountered a virtual surface. And I consider drones in this category of encounter-type haptics. These all have limitations once we use them for haptics in VR, whether it would be the accuracy of how they're presented in space, where the haptic sensations are being rendered, or the resolution of the surfaces that they're rendering, the speed, the delay. All of these limitations exist within these categories. And the insight that I drew on in my PhD was that the human perception is imperfect, so we don't need to create these perfect, realistic haptic renderings. So to demonstrate this, I'm going to ask everyone, you get one shot at this. I'm going to ask everyone to touch your 2 index fingers together above your head without looking. You get one shot. I think the sides were demonstrating my point, which is what you're doing in this task is you're using your sense of proprioception, the forces in your arms and muscles telling you where your fingers position in space. And this is a very noisy signal. You don't actually know very accurately when where your finger is. And this leads to a lot of fingers crisscrossing like I saw a minute ago. So this is what I mean by the human perception is limited, and we can, the kind of insight here is that we can leverage these limitations to make our haptic devices appear as if they work better than they actually do. So to demonstrate this, I'm going to first talk about the drone project and how we use the limits of human perception to make the drones appear as if they were more accurately positioned in space. And I'll show you another example where we use shape displays for haptics. And shape displays are matrices of actuated pins that go up and down, and they can render different surfaces, 2.5D surfaces. And I'll talk about how we use similar illusions to make shape display appear as if they were higher resolution. And I'll use this slide as kind of the outline for my talk. And this first half of my talk will be around these visio-haptic illusions that improve the perception of haptic devices. And then in the second half, I'll talk about how we use augmented reality for interacting with robots to both extend people's abilities in the physical space, so not virtual reality, and also provide explanations of robot capabilities and limitations. So let's start from the first project. Going back to what I talked about earlier, we had different fabrics attached around the drone. So depending on what fabric you were touching, it would rotate and present you with velvet, silk, or other fabrics. We could attach different 3D printed props to the drone itself. And the drone was also a box that we were using in the simulation. So we were using it as shoe boxes here, and the drone basically could fly to different surfaces, land, and present the shoebox to the user. You may be wondering at this point, do people even feel comfortable touching a drone? If any of you have interacted with drones, people are not necessarily comfortable being super close to a drone. And so I was curious about this. So before doing the project, I mentioned we ran a user study where we had participants come and we had a between subject study design. So half of the people interacted with a regular drone, and the other half interacted with an earlier version of our safe-to-touch drone. So it had a, at the time, wooden mesh cage. And this was an elicitation study. So we didn't tell people how to interact with the drone. We just gave them an image of before and after of what we wanted to accomplish. And what we saw is that in the regular drone condition, most people use gestures and voice commands. So they would do things like take off, land, go further, take a photo, things like that. But in the safe-to-touch condition, more than half of our participants actually physically touched the drone and picked it up, pushed it away. And that was kind of encouraging that without us even prompting, users felt comfortable. Once you had this meshed cage, users felt comfortable being close and touching the drone. So ideally, what we wanted in this application was that as the user reached out to touch a patch of a fabric, we wanted the drone to be precisely positioned in that point. But what really happened because of the meshed cage and all these fabrics and the props that we were attaching to it, sometimes there would be a slight offset between where the drone was and when we needed it to be. And there was also some drift here. And of course, we could try to improve this, but I'll show you that this is kind of more broadly about how do we make systems that are simpler and less complicated and more affordable using these illusions. So the problem here is that the drone was kind of drifting or offset from where we needed to be. And we were inspired by this paper at CHI 2016. It was called Haptic Retargeting, and they had stationary users with 3 stationary cubes. And what they were doing is they were doing a kind of a magic trick where 3 virtual cubes were presented by 1 physical cube. And so we wanted to kind of figure out how does this work and how can we make it apply to a system where the user is moving around, the drone is moving around, and can we apply this dynamically on the fly? And of course, I'm assuming a lot of you are roboticists in this room, and so you probably know about optimal controller. But here, what the point is that we were able to look at how the human brain plans and controls movements. And the short answer is that the brain is an optimal controller. If you're not familiar with this, I'll briefly talk about this. So let's say I want to reach out and touch this bottle over here. What happens is that my intent is converted to motor command signals that are then sent to my body. But this is subject to noise and disturbances in the environment, so the brain has to figure out a way to estimate what actually happened in the physical world. So I use, as I move, I use my sense of vision, for example, or my proprioception, and these sensory apparatus, basically using sensory signals to estimate where my hand is in space. So that includes looking at my hand and also feeling the forces in my muscles and arm. And all of the sensory signals combined give an estimation of where my physical hand is, and the brain uses where it expected the hand to be and where it actually is to kind of update the signal on the fly. So we know this about how human brain plans during end-to-end goal-directed reach, and we were leveraging this in this case. And the way I think about it is basically virtual reality is a medium that intercepts our sensory signals. So you have the physical body, I'm holding the controller, and this allows us to track the user's hand. And this sensing and tracking is then converted to motions of the virtual avatar. So it's basically intercepting, tracking the movement, and then intercepting the visual sensory feedback and overwriting it with whatever I'm seeing through the headset. And this gives us an opportunity to create mismatches and remappings instead of having a one-to-one mapping. So we get proprioception from our physical, real hand, but visually we're seeing our virtual avatar and not our real hand. So here, what we did for this project, we call this technique dynamic retargeting. And as the user was reaching out to touch the drone, if the drone drifted away in one direction, we would drift the user's virtual hand in the opposite direction. And so because the human brain is an optimal controller, your brain would be like, OK, my hand is going further right than I expected. I need to correct for this. And it would send motor commands going in the opposite direction. And if the discrepancy here is small enough, people don't even notice that we're doing this. And if we gradually do this, people don't notice that we're doing it. And the reason this works is I'm going to ask everyone to do the same task again, but in front of you, in front of your eyes. Again, you get one shot. Try to touch your fingers. OK, no more audible gasps, so I'm guessing everyone's successful at this task. And this is exactly because of the fact that your proprioception was noisy. You didn't really have information about where your finger was, but your visual signals are more certain. And the brain knows this and basically weighs whatever you're seeing over what you feel. And so in this case, if there's a slight discrepancy between proprioception and vision, the brain believes what it sees over what it's feeling through the muscles. And this is known as the visual dominance effect. So by doing this, we were basically able to have people come to the lab and try this e-commerce application. Everyone was able to touch the fabrics, pick up the hanger, even though the drone was not great. And this is because we were able to do these dynamic retargetings. And whenever the drone drifted, we would basically trick people into making contact with the drone at a slightly different position than it actually was. And, that their virtual hand was. But it also showed us some limitations of this technique as we were trying it out with people. Specifically, if the hand was moving really fast or if the distance to the target was small, then we didn't have enough time and distance to gracefully and gradually add this redirection. And people noticed that we were messing with their senses and we were warping the space. And similarly, if the drone was moving slowly in one direction, it was very easy for us to retarget the hand. But if the drone was moving fast and changing directions, that was creating this constant remappings of space, and people would notice that we're doing these things. So in the follow-up work, where we were using a tabletop robot for haptics, so the goal here was we have a virtual controller control panel that's very large, but we want to have these haptic interactions where you can press buttons and move physical knobs. And instead of building a whole virtual panel, you can have one small robot with one of each kind of item on it, and it can move around to give you haptic feedback. But the problem is if you're moving really quickly and interacting with different parts of the control panel, the robot can't keep up. And so the limitation here was the speed of the tabletop robot. And so in this project, what we did was we used the direction of the hand movement, the speed, the gaze to predict which target people were interested in interacting with. And we were also using the minimum jerk model, which states that people try to minimize the acceleration as they're reaching in these goal-directed reaches. And using that, we were able to predict the estimated time of arrival. And we, of course, know our robot's limitations and roughly the maximum speed of our robot. And that allowed us to basically predict how close can the robot get before the user makes contact with it. And we were able to do this dynamic retargeting when it was appropriate, when we had enough time, when the distance was small, and when the distance was large or the speed of the hand was too large, we chose not to apply retargeting and accept the fact that sometimes there would be a delay in when the robot arrives. So it gave us some predictive power, and we used it to make a decision based on whether or not we should apply an illusion. So I want to talk about another example of a project where we used these limits of perception to improve the performance of a haptic device. Here I'm showing a shape display, which is a matrix of actuated pins. Every pin has a motor that basically allows it to go up and down, and it enables rendering of 2.5D surfaces. And here we're using it for haptics in virtual reality. As you see here, the resolution of our shape display was not great. And here I'm trying to trace this pentagon maze, and my finger keeps getting caught in these pins, and it's not a very smooth surface for me to trace. And of course, since then, there have been much higher resolution shape displays, but there are all sorts of reasons why you may not want to increase the resolution here. This was a relatively affordable shape display. The smaller the pins, the higher the price. Depending on the technique you're using, you may not be able to apply as much force. And so we wanted to think of ways to leverage limits of human perception to make shape displays work as if they were higher resolution. And so to do this, how many of you here remember using Microsoft Paint? OK. More than I expected. But if you remember in Paint, when you draw a line at an angle, you would see the pixels on the screen. And that's basically a similar kind of rasterization problem we're having on the shape display. And we were thinking, what is like an equivalent of anti-aliasing when it comes to a rendering on a shape display? So whenever we had a line at an angle, we decided to instead render a horizontal line. And we would apply the similar trick where we're basically shifting the user's finger up, and as a result, they move their physical hand down. And so this creates an illusion. I think I said that backwards. But basically, we do the opposite of what they're visually seeing, which results in them ultimately moving their physical hand upwards and following a line that is horizontal, smooth. All the pins line up really nicely. So it's the same kind of trick of displacing people's virtual finger, but instead of during reach, we're talking about these sorts of contour following haptic tasks. What we were interested in is how far could we take this illusion before people notice? as you might imagine, the larger the angle, the forces in the angles in your fingers and wrist might give away the fact that you're actually touching a horizontal line. So to do this, we ran a user study. We had people come to our lab, and we used the method of constant stimuli. So they tried a lot of repeated samples, some of which did not have any illusion. So they were tracing the same virtual line in the physical space. And some of them, we applied an illusion. So they were visually seeing a line at an angle, but they were touching this horizontal line. And so these are the results that we got. This is a classic kind of psychometric curve, S-shaped curve. And here on the x-axis, I'm showing the angles that we tried. So we tried 5, 15, 25, 35, and 45. And on the y-axis, I'm showing the ratio of repeated samples that a user said that they noticed an illusion. So it's the ratio that they noticed that we were doing some remapping. And as you might imagine, the larger the angle, more people noticed that we were applying an illusion. The point of conservative detection threshold is at 50%, and this is when half the time people tell us that they notice and half they don't. So they're just about to notice that we're kind of applying a remapping. And 75% is used in these psychophysics tests for the point at which most people, most of the time, notice the illusion. And here we found that around 49.5 is when people notice, which is great, because after 45 means that we can remap every line to either a horizontal or a vertical line. We wanted to also know that now that we're applying these illusions, does it actually help improve the interactions with this haptic device or not? So we ran a follow-up study with a new set of participants. They didn't know anything about illusions. And what was really nice is that they were in VR, so they couldn't see the shape display. So we could tell them that we had 2 different shape displays. And we used the method of 2 alternative forced choice tasks. And we asked them which one of the 2 displays they thought was smoother, higher resolution, and what they preferred. In reality, they were both the same shape display, but one was applying the illusion and one wasn't. And here are the results for 40 degrees, which is the largest angle we tried below the detection threshold that we had. And this is aggregated results across all of our participants. And we found that in most repeated trials, participants thought that the case with the illusion was higher resolution, smoother to trace, and also the one that they preferred to interact with. So this showed that, and no one in our study mentioned anything about remapping their fingers or having experienced any illusions. And it shows that we were able to leverage this to make the interaction with this haptic device better. We got similar results for 10, 20, and 30 degrees. And I'll show you one more example of an interaction we tried, but won't go into too much detail. So here I'm rendering a semi-sphere on the shape display. And as you can see, there are only a few pins in that area. So the elevation change is pretty drastic. And again, my finger keeps getting caught in these pins. And so what we did instead is we kind of blow up the rendering on the shape display. And we're changing the speed of the user's finger. So if any of you are familiar with the control to display ratio gain on the computer mouse, when you control the mouse, the cursor moves faster. That's exactly what we're doing here, but with user's virtual finger. And this allows us to basically have more pins in that area. We can render more details, and the surface is also smoother. We did a similar follow-up studies. We found that given our constraints of our shape display and the dimensions that we had, we could blow up the kind of enlarge the rendering by 1.9. And we also did the follow-up study and found similar results where we saw improvements in preference and smoothness and resolution. So using this method of angle redirection and scaling up, we were able to improve the perception of this shape display as a haptic device. Yes, Radhik?
So people didn't, sorry, maybe I misunderstood, but people didn't realize that they were touching something?
No. So these psychometric tests have this S-shaped curve, and in the middle is where people start to notice. And so as long as you stick below, especially the 50%, people don't notice that you're doing anything. And as you see here, the error bars are pretty large. These are 95% confidence intervals, and that's because people were widely different. Obviously, me as a computer scientist sitting behind my computer all day have a very different sense of proprioception than a ballerina who dances all day. And so there was some variation across this, but 40 degrees, for example, for the angle was a point where most people don't notice. Great. Any other questions for the first half? Great. So in the first half of the talk, I was talking about using the limits of human perception to improve the perceived performance of haptic devices when used in virtual reality. In the second half, I'll talk about how we're bringing some of these illusions to physical spaces. And the first project I would like to talk about was presented at WIST 3 weeks ago, and our goal here was to extend people's abilities in physical spaces. And one of the inspirations here is there are tons of decades of research in virtual reality on interactions that extend people's abilities in VR and take advantage of the fact that you can remap people's movements to their avatar. So one example of this is the go-go technique, which was presented at WIST in 1996. And the idea here is that there's no reason we should be bound by the limitations of our physical body in virtual reality. So your virtual avatar's arm can grow as long as you want it in order to pick up a virtual object. And since then, there have been lots of studies on understanding how the human brain's plasticity can adapt to these remappings, and how far can your arm length grow before you lose control and can't adapt to this interaction. So we wanted to bring this go-go technique to physical spaces. And this is work done by Mokari, who's sitting in the back by the door over there. And he did an amazing job with this project that I'm presenting today. And the idea here was, how can we allow people to manipulate far objects in the physical world? So here we're using a pass-through augmented reality. So you're still seeing everything that's physically around you, but it's being fed through the cameras on the headset and re-rendered on the headset. So the idea here is that you can reach out. Obviously, we can't make your arm length grow, but we can create visualizations that give you similar power. We're instantly deleting the real object and rendering a virtual twin using Gaussian splatting in your hand. And then you can place that object on any surface and let it go, and it would land on that surface. And this we call reality go-go, which brings this idea of manipulating far objects to physical spaces. But of course, you don't have to have a physical source that you're manipulating. It can be something in your fridge. It can be something you're buying online. And the idea here is that you can have these, we can extend people's abilities and allow them to instantly materialize these objects into physical space. Of course, if I have a coconut water or a bag of chips, I want to consume it. And so haptics here is not very helpful, because it's not about feeling the sense of touch. I want the actual object so I can consume it, right? And that's exactly what we did in this project, which we call reality promises. So this is a reality promise that we create through the interaction. And the idea is, how can we then allow the person to actually pick up that object after the reality promise has been created? So you can go about your day, continue your task, and once the counter ends, the object is materialized, and now you have a physical coconut water that you can drink from. I'm not sure if there was actual coconut water in this, but Mo's acting is great. And I'm going to show you behind the scene. This is Mo in my office, and I'll just let the video play. So here the idea is that a robot can fulfill the promise and catch up reality to what you're visually instantaneously seeing. So I'll talk about two pieces of most system that makes this possible. First one is Skynet, which is an interaction synchronized robot control. And basically, we put the headset on the robot, and this allowed the robot and the person to share the same map and understanding of the physical environment. And so when an object is dropped, we have the grasp for the robot, and we can send the waypoint to the robot to navigate there and grasp the object. And the state machine kind of keeps track of this. And what's really nice is that we can predict how long this will take, roughly, and that informs the countdown and the progress bar to give users feedback so that they know when an object is real versus not. And the second piece of this is on-device Gaussian splatting that we're doing that's aware of where the robot is. And this is also used to delete the object in the first interaction that I showed. So here is my office, and the scan of the office with the iPhone allows for rendering on headset. And this is all running on device. There's no tethering or streaming to the device. And here's a flashlight showing a virtual copy on top of the real copy. And this allows, for example, Mode to delete Lauren from that view. And because we know where the robot is and we have these control points of the arm and the robot, we can create a cone from the user's headset that only renders the Gaussian splat points behind the robot in front of it, or in the case of the object, the points behind the object in front of it. And then feathering the results allows for the robot to be hidden from view. I want to give a shout out to Cyrus. I don't know if he's here, but he's worked on a Gaussian splatting toolkit for XR, VR, AR, VR, and extended reality applications that he'll be releasing soon. So if you're interested in any renderings in VR, check out SplatXR and Cyrus's work. So putting it all together, you can use Reality Go-Go, grab an object. Here, we're not deleting the original. That's another interaction that we talk about in the paper. And you can place the object on any surface that the robot is able to place the object. And by dropping the object, that creates a reality promise, and then the robot can fulfill. And so this interaction is called dematerialization and rematerialization. So the physical cause of motion in this promise is the robot moving the object. But the virtual cause in this case is the Reality Go-Go interaction. But you can imagine you can swap it for any other interaction. For example, you can have a virtual character whose actions now will have physical effects in the world. So here, a bee can pick up the chip and bring it to you, and creating a motion path that diverts the user's attention from the robot allows the interaction to ultimately meet at a point where the robot places the object exactly where the bee drops the virtual copy. Yes?
Can I just clarify something? So I guess when you're deleting some object, you're segmenting, like you're creating some segmentation mask and then rendering stuff that's kind of behind that?
Yes.
Is that the idea?
Yes.
Do you have issues with the segmentation at all, or does that work?
So in this example, everything's annotated manually.
Oh, okay.
So I'll talk about kind of the future work and limitations, which is how do we then go from not only segmentation, but also can we create this Gaussian splat from the headset directly so we don't have to capture the room in advance. So this is a really well-known quote by Mark Weiser, who's widely regarded as kind of the founding people who founded the field of HCI. And this quote says that the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they're indistinguishable from it. And I think in this project, Reality Promises, we took a playful take of this and took it literally to mean that the robot can disappear and you can expose the capabilities of the robot through these interactions with the physical world. But the idea here is that the technologies that are that can extend our abilities, augment our intelligence, can go in the background, and they don't interfere with how we interact with the world. And so in the next project, I'll talk about how, without deleting the robot, this sorts of object-oriented interactions give us some capabilities in terms of how we can not only instruct robots, but also give users explanations of robots' capabilities and limitations. So this work is currently under submission. And I want to talk a little bit about kind of the continuum from VR to physical reality. The first few projects I showed you were fully in virtual reality. Everything was virtual. And Reality Promises was using pass-through AR, where we're using cameras on the headset to allow you to see the physical world. But it's difficult to do these types of deleting the object or the robot when you get to optical see-through AR, where you have glasses and you can only render lower opacity pixels. You can't delete every pixel through the video feed. And so the ideas here still apply once you get to these light form glasses, but maybe we can't delete the robot, but we can use these sorts of interactions with objects as a way to interact with robots. So here's Lauren, my PhD student, who presented this poster at WIST a few weeks ago. The idea was that you can use virtual copies of physical objects. And here, a lasso selection allows you to snap objects to their default locations that have been stored as a way to instruct robots to place them back in the shelf. But I think what's more interesting than the instruction of the robot is this bidirectional communication that these interactions enable. So the affordance of the virtual twin then becomes, can encode the capabilities of the robot. And for example, as you pick up an object, only objects that can be picked up or grasped by the robot will be movable through this direct manipulation. And objects that can't be moved, we can use visualizations that communicate why the robot is unable to grasp and manipulate them. So here, objects that, for example, are too high or too large or heavy can be marked as such. And the idea here is that the user never actually interacts with the robot. All interactions are done through this object-oriented paradigm. So how Lauren is doing this is she's using the pass-through camera. But again, for this project, you don't need the pass-through AR glasses. You can do this in optical see-through because all the ghost objects or virtual twins are lower opacity, and we're not actually replacing any pixels one-to-one. But she creates this representation of all the objects and their capabilities, and she also has a full 3D model of the environment that she's in. And this allows her to create this simulated environment in Unity to generate these ghost objects, encode the capabilities of the robot, but also have this sort of loop that always can decide whether or not the action can be completed. So I'll show you 3 examples. Here, Lauren is recording. The first one is when an object is manipulatable, you can see the signifier, the circle, and then you can grab the virtual twin, place it somewhere else, and we have a lower opacity virtual model that you can move around. And then you can create a sequence of actions, and as soon as the placement, for example, is not possible, the object turns red, and you get an explanation for why you can't place or leave the object there. And so once the commands are sent to the robot, this is using Skynet from Reality Promises that sends the commands to the robot. Here's another example. And what I like about this is both shows multi-object manipulation here through a lasso selection of the physical world, but also it enables some sort of a mixed initiative interface for people to help the robot as well. So when an action is not possible, either the system can simulate an alternative, give users an alternative, or have information that can help the user either virtually or physically help the robot in this case. And so there are other examples we talk about. For example, if you're picking up a cup that can't be reached, showing a different cup on a different shelf is an example of an alternative that's shown to the user. And finally, this also enables beyond pick and place of single object or multi-object. You can also show higher levels of abstraction. So if I want to select this curtain, I see all action possibilities on the controller. But if I pick, for example, one option, brighten, I can see that the robot can't reach that. But if I pick draw, then I can use the direct manipulation to specify a spatial parameter that's useful here, in this case, how far you want the curtain to go up. And then I can send the command to the robot. So if an abstract action does not have a missing spatial parameter, you don't necessarily need to do any direct manipulation, but anything like pick and place or filling a bottle or drawing a curtain that has a spatial parameter that you could specify can allow you to do this. So there are, of course, a lot of open challenges here. We have a limited set of constraints that we're working with. A lot of them are static, like the properties of the object or limitations of the robot in terms of how fast it can go or how high it can reach or how far the arm extends and things like that. But of course, there are a lot of more interesting real-time simulations we could extend the system to. Also, as you mentioned, the scene is captured in advance and annotated. So the next step would be, how do we go about capturing the scene and creating the model on the fly as the user is walking around with the glasses? And can we do the segmentation and reconstruct the scene, allowing for these interactions to happen on the fly? And this is interesting also for remote teleoperation, because the user can then become the robot itself and directly manipulating things in VR, a virtual copy of the physical system, as a way of not only instructing, but also receiving explanations on the fly. And if the model updates in real time, it allows for the robot then to perform those actions. Something I'm curious about for folks here is whether or not there are opportunities for these types of object-oriented interactions to inform robot learning over time. And specifically, for example, I can think of the direct manipulation can be constrained by the trajectories that are possible, and maybe those could be used as a fast way to get user preferences elicited through the interaction. So today I talked to you about two projects that used robots and virtual reality, and using specifically robots for haptics in VR. And the idea there was that we can use the limits of human perception to make these devices work, make these devices appear as if they work better than they actually do. And the second half is using augmented reality. We can extend people's abilities and create interfaces that make human-robot interaction more explainable. I want to talk a little about a few projects that are very early stage, but the idea here is that I don't necessarily believe that all of our interactions with robots will be object-oriented. There are cases where this may be appropriate or preferable, but there are cases where maybe we have glasses that have cameras, but they don't have a visual display. And even then, there are interesting questions that we can ask of how do we enable interactions with robots in physical spaces when we have this egocentric view of the user. So I'll talk about 3 projects we're working on, again, early stage projects, but I think given that I'm at Princeton, I thought it would be interesting to share. One project is about how can we understand implicitly from what the user is doing when they need help. And of course, we're thinking of this in the context of a virtual agent giving instructions to the user, but you can imagine the robot could step in and then help the user similarly. So we annotated an existing data set, HoloAssist, that basically has 2 people. One person is building things like IKEA furniture, and there's an instructor in a different room. And the instructor sometimes decides to interrupt and proactively give the user instructions. And we were looking at those instances and finding what is about what the person, the instructor, is seeing through this egocentric view that makes them feel the need to interrupt and help. And of course, there are obvious things like pausing or hesitation or explicit queries like, what do I do next? But there were a lot of instances we found that there were no pausing or hesitation, but yet the instructor decided to interrupt. And we annotated all those instances and found different categories of implicit movements that made the instructors interrupt. And so we're working on kind of detecting these points of user uncertainty and leveraging them not only when they're paused, but also as they're moving through actions to decide when someone needs help. And again, you can imagine the robot stepping in or showing some virtual instruction on what to do next. Other than implicit understanding of intent and uncertainty, we're also interested in inferring users' instructions that are explicit, not necessarily through direct manipulation and object-oriented interactions, but the same way we interact with someone else through gestures, language, gaze, and things like that. So what we were interested in is there's a lot of literature on how people communicate through, specifically in human-robot interaction. How can people instruct a robot through language or at best pointing? But the way we communicate with each other, our gestures encode a lot more information than just pointing. And so what we did is we brought pairs of participants to our lab, and they worked on building Lego blocks together. I'm going to go back. So the instructor was in one room, and they could see a virtual target tower, and they were instructing a builder in a different room. And the reason we used AR in this design was that we wanted to isolate just the voice and the hand gestures. So we didn't want people to see each other's facial expressions, body language, in order to help us really control this experiment and model what was going on. So the builder could only see the instructor's hand and hear their voice. And what we found was very interesting. So let's say they were building this C-shaped tower together. What we found was that in the very first trials, so there were repeated trials where they were working together. In the very first trial, people were very explicit. Often the gestures were redundant in the sense that you could just listen to what people were saying and you could reconstruct the tower. But as trials went on, people's language became very ambiguous. So they would do things like put it this way and use hand motions, strokes, pointing, all sorts of gestures to complement ambiguous language. So if you were only listening to what they were saying, you could not reconstruct the tower. And that allowed us, this parallelism allowed people to be much more efficient over time. Another source of efficiency was that people formed conventions with each other. So they would say, this forms like a C-shaped tower. And the next time they saw a similar shape, they would either say, put the tower like this, so it would be ambiguous language complemented by a gestural convention, or they would say, put the C-shaped tower over there. And so this allowed people to chunk instructions together and become much more efficient. And these are things that our current systems don't support. Whenever we have an interaction with a system, it's often predefined static over time. And so our goal for the next steps in this project is how can we build agents that are both convention aware, that can keep up with people as they have repeated interactions and they build these conventions together, but also propose conventions that make interactions more efficient. And then finally, another example, let's say you do have lightweight glasses with minimal display. There are also opportunities for AR to help human-robot interaction, not necessarily through object-oriented interactions, but through communicating ambiguities to users. So here, if, for example, someone is soldering and they want the robot to bring them something, their hand is full, so they're using gaze to say what they're looking at, and the uncertainty, the robot is unsure of which drawer they want to be picked up. We can visualize the uncertainty through these triangles that you saw and allow the person to either confirm or move their head to adjust the pointer and clarify. Here's another example for placement. So if I say put it beside the plant and there's some ambiguity on which side the object should be placed, we can expose that uncertainty and allow people to disambiguate, for example, using voice here by saying A or B or C. And sometimes it doesn't matter, and so the question is, when do we want to expose these points of uncertainty, and how do we allow people to use multimodal signals like voice or gestures or head movements to disambiguate and clarify to the robot. So I want to leave some time for questions, but I think I want to end with when we think of computing and when personal computers became widely used at our homes, really that was in part, or I'm curious what people here think, if you didn't have the mouse or a graphical user interface, it's unlikely that everyday users would be using the terminal to interact with computing. And so thinking about the interface and the input really helped computers come to our homes where everyone, not just expert computer scientists and engineers, are able to leverage them. So in my group, we think a lot about, as computing becomes more distributed and situated in physical spaces, when we have wearables and robots and IoT devices, what is this next kind of paradigm of interaction that is going to make robots, for example, come to our homes, and not just experts, but everyone to interact with computing. I want to also shout out that we have a speaker coming on Monday who also works on similar things, but she has a different take. And I would encourage you to come to the CS seminar on Monday at 12:10 and 105, Alex Ion. And thanks to all of my students and team members and collaborators and funding sources. Great, happy to take questions.
Wonderful, thank you so much, Parastoo. And we have a few minutes for a couple of questions, so let's see.
Hi, thank you so much for such an interesting talk. My question was related to maybe the drones, but also the robots, like moving objects around. Robots are pretty loud, so how do you guys get away with or does the fact that the robots are quite noisy interfere with the human experience?
Yeah, that's a great question. So in the study with the drones, we had everyone wear noise-canceling headphones, and that works really well for drones because the frequency is very easily canceled out in the noise-canceling headphones. And the reason we did that was we didn't want people to use the sound as a way of estimating where the drone is. And so it was part of the study design. But the thing that we couldn't cancel out was the wind from the drone. So you could actually feel the wind when the drone would get close to you. And this was something we were worried about, but the participants that came to our lab actually liked the wind as a form of ambient feedback, telling them where the drone is in space. So when they couldn't feel the wind, they would move really quickly in VR. And when they were feeling the wind, they would be a little bit more cautious with their movements, which helped us and made the study safer. But I think there may be a similar effect in reality promises. And we didn't study this, and I'd be curious to know. But I wonder if the slight visibility of the patch is actually useful signal as a way of ambient kind of information to tell people where the drone is and making them feel safer. Whereas if we were to fully make it invisible, which I think could do in the future, that might create this sense of uneasiness. But that would be interesting to study in the future.
Hi, thank you for the great presentation. I'm curious about how the trajectory right now is currently being computed and how the robot follows the path, and how that might change if you want to shift towards real-time scene reconstruction.
How does scene reconstruction influence the real-time paths? Is that?
Yeah, how the trajectories are currently being computed,
right?
And if it's pre-computed, and then how that might have to change if you are now trying to construct the scene in real time.
That's a great question. So the trajectories are not pre-computed, but the scene and the objects and their positions are static and known in advance. So what would be really nice is as you reconstruct the scene on the fly, then people can actually move objects around and you can track where objects are going and you can update your model of the world in real time. And that would allow you to allow the person to also move things, not just the robot, and you would be able to enable these interactions still and create the trajectories on the fly. Yeah.
I'm thinking of so many ideas.
Great. That's what I was hoping for. And I would love to collaborate with.
In the reality promises, I was actually just wondering if you had thought about collaborating. You probably have with industry. So when I look at this, the idea of an invisible robot moving around in my office with me in it is not actually appealing.
Right.
I was like, that is a little creepy.
Yeah.
And has lots of connotations I don't like. But the opposite, where it's like we have this lab in Forrestal, and I keep thinking I need to go there and clean it up. If there was a robot there, and I could literally move things around, have it be happening, and sort of manage remote spaces.
Right.
It seems like that would just warehouses and stuff where we're leaving people, which is a terrible job to be left alone in these very dull spaces.
Right.
Whether you think this could extend to that kind of like warehouse
for sure.
management or remote lab management, for example.
Yeah. I think remote teleoperation is really an area I'm really excited about, because you could put on your headset, go to a virtual duplicate of, especially if we track it in real time at that instant, and you can do all these lasso selection, move things around, and the robot can basically be your eyes. You can even move around and look at different places, and the robot could use its camera to update your direction. Or you can simulate it if you have a fully reconstructed scene. And then you could have these object-oriented interactions, and then you could sign off, and then the robot would catch up reality to what you instructed, and then you can go back and see the results. And yeah, I think that would be, and I don't think it would be replacing people. It's allowing people to be more efficient and organizing multiple spaces in a short period of time. What I like about these direct manipulation interfaces is also whenever you really care about the position and orientation of the objects and how they're placed, that's really useful. When I say place the coconut water here, I can't specify the exact orientation and position as well. So I think those applications where those spatial parameters need to be specific are also great for this.
Yeah, it seems like I'm only thinking of Forrestal, which we have to drive there and do things, and then there's so much to do when we're there. But if like you could do it offline, but yeah, it seems. I guess in your case, the reality promise argument is that for some reason you want that to become real within the time of that interaction,
right?
Which I guess is a little bit different from the remote teleoperation where I
I think the object-oriented HRI paper is probably closer to what you're describing.
Sorry, because I come from a healthcare background. One of the biggest challenges in hospitals is OR room turnover. And between the staff, like I love what you said. It doesn't replace people. It makes people more efficient, and I see that. And then like reduction of infection and bacteria transfer and all those things was just like a quick real-time application. That when you're talking about like industry partners and like what are they thinking about? They're thinking about profit. And one of the biggest profit drivers of these massive hospital systems, especially since we're on the Northeast, is surgery turnover and how quick can we do surgeries.
Yeah, that's interesting. Thanks for sharing.
So in the go-go reality scenario, is it important at all to know the texture of the object you are grabbing? Probably for the coconut juice, because you know the object. It's not important at all to feel the texture of the object.
Right.
But can you imagine a scenario that feeling the texture of object is important?
Yes. I think the first half of the talk, the VR, any VR scenario, I think you would want to feel the texture of the objects that you're interacting with. And I think there are data sets of, I was visiting UPenn last week, and there's data sets of inferring texture from visual data. And I was super excited about that because I think haptic rendering can really benefit from knowing the texture of objects. And then if you have gloves that can vibrate and render different textures, that gives you one more sensory information that you can interact and improvise with virtual objects. Yes, super interesting.
Thank you.
All right, awesome. We unfortunately have to cut it here because Parastoo actually has to run to the next event. But let's thank Parastoo once again.
Thank you. Thanks for having me.